Hi there. For this video, we'll be factoring higher order polynomial equations. So in the previous video, we note that the rational root test is a great way. It is very straightforward, but it is very time consuming as well. So in this video, we'll try to apply the previous factoring concepts that we know and previous algebra concepts in general to be able to solve higher order polynomial equations much faster. So basically, our goal here is to factor the polynomial, the higher order polynomial, into its linear factors. So why linear factors? Well, when we achieve a linear factor, this cannot be reduced anymore, or we can't factor this anymore, which means that it is easy to solve the value or the root in this case. Just like in quadratic equation, if we have, say, this and this factors into x minus alpha times x minus beta equals 0, we immediately know that this is simply x minus alpha equals 0, x minus beta equals 0, or x equals alpha, or x equals beta. So we'll apply the same idea in this one. Let's first have x raised to 6 minus 3x raised to 4 minus 4x squared equals 0. So in here, first, we observe that each of the terms in this equation has a factor of x squared, a common factor of x. So we can factor that one out to obtain x squared here times quantity. What's left inside is x raised to 4 minus 3x squared minus 4 equals 0. Next problem is, how do we factor this one out here? Well, by observation, you may notice that it looks like a quadratic equation. Indeed, if this is a square and this is just non-existent out here, then we have x squared minus 3x minus 4, which is easily factorable in quadratic terms. So how do we make that possible? Well, we can use substitution. We can let y be equal to x squared. So we'll obtain x squared times x raised to 4 will become y squared. Since if we square this both sides out here, it should be like this. If we square this both sides, we'll obtain y squared equals x raised to 4. Minus 3 times y minus 4 equals 0. Now that it's a quadratic equation, this now is easily factorable. So you can verify by your knowledge on factoring quadratic trinomials that this quadratic trinomial out here factors into y minus 4 times y plus 1. And from here, note that since it is a linear already, and we can't really reduce it anymore, we can now go back to x squared. So bringing it back to x, we'll have your x squared times x squared minus 4 times x squared plus 1 equals 0. So this is what we have so far. From here, observe that this one out here is a difference of two squares. So we know that this factors into x squared times x minus 2 times x plus 2. How about this one? Note that we can't really simplify it anymore. And if we try to, we'll actually obtain a imaginary root. Indeed, if we try to apply difference of two squares here, we can write it as x squared minus negative 1. And then we'll have here x minus square root of negative 1, which is I, times x plus I. In either case, it is not a real root. So we leave that one. We leave that one as it is. So we have here x squared plus 1 equals 0. And now, we have fully factored the polynomial. We have here x squared. Note that we don't really need to factor this since it will just give us x times x. Then we have x minus 2, x plus 2, and this one, we leave this one as well. So, the question now is, like in quadratic equations, when will this equation hold? This equation will hold if either this 3 is equal to 0. So that is x squared equals 0, or x minus 2 equals 0, or x plus 2 equals 0. Solving these equations, we'll obtain x equals 0, or x equals 2, or x equals negative 2. And these are our final answers. So as you can see, it's also quite a lengthy process, but compared to the rational root test, it's much better and much faster. Let's have this next example. Let's have 2y raised to 4 plus y cubed minus 19y squared minus 9y plus 9 equals 0. And note here that we can't really factor anything. We can't also substitute anything out here. So, how do we factor this one? Well, we can apply a part of the rational root test, but it won't end there. So by rational root test, you can verify that a possible rational root out here is negative 1. So how did we arrive at that? You may check out the previous video since I put out a similar example. It's actually the same example wherein we showed the possible rational roots of this equation. And after this, we apply factor theorem. By factor theorem, you may also verify that y equals negative 1, or basically this is a factor of this polynomial equation. How? Well, what you'll do is you'll substitute this value to this equation out here, or expression. So you'll have here 2 times negative 1 raised to 4 plus negative 1 cubed minus 19 times negative 1 squared minus 9 times negative 1 plus 9. And upon simplifying this, this must be equal to 0. So basically that's the factor theorem. And so we know that y equals negative 1 is a root. If we try to apply the rational root test, we'll just simply repeat this process. But for this one, what we'll do is after finding one root, which in this case is y equals negative 1, we will apply synthetic division. So we have here y equals negative 1. If you don't know synthetic division, you can check out my previous video on that one. I'll put it somewhere, probably on the top right of the screen. So applying synthetic division, we'll have here this value, negative 1. Then we write out the coefficients of this one out here. So we have here 2. Coefficient of y cubed is 1. Coefficient of y squared is negative 19. Coefficient of y is negative 9. The coefficient of the last term is just a constant, so we have 9 here. First step is to bring this one down. So we have here 2. Then we keep on multiplying this by this. So 2 times negative 1 will give us negative 2. Add this 2 up, and we obtain negative 1. We then repeat the process. So negative 1 times negative 1 is 1. Negative 19 plus 1 is negative 18. Negative 1 times negative 18 is 18. Negative 9 plus 18 is 9. Negative 1 times 9 is negative 9. And 9 minus 9 is 0. What does this mean? This means that y minus 1 divides this, and the quotient is this. Note that this quotient out here, to get its exact value, we simply add the variables. So we have here y, and the degree is minus 1 of the degree of this. So we'll have here y cubed. This is y squared. This is y, or y raised to 1. And this one is simply y raised to 0, or we can remove it. So this is our quotient for that synthetic division. And now, recall that to obtain this in division, if we have if we have a value out here, and out here, so the quotient, the divisor, and the dividend, we can express the dividend out here as b equals a times c, or the divisor times the quotient. So, applying that same idea, we can write this, the dividend in this case, as divisor, which is y equals negative 1, or y plus 1 equals 0. So we have here y plus 1 times this quotient out here, which is 2y cubed minus y squared minus 18y plus 9, and equals 0. And so we have factored out the higher order polynomial equation that we have above. Now, the next step is we could either apply the synthetic division again, or observe this. Note that by our knowledge in factoring, we know how to factor 4 terms. So, we can write this one as y plus 1, and this one inside. Observe that if we pair this one up and this one up, we can factor y squared in the first pair to obtain 2y minus 1, and we can factor out negative 9 rather, in the next pair to obtain negative 9 times inside we'll have 2y minus 1. And since we have a common term, if we treat 2y minus 1 as a term, a single term, we'll have here y plus 1. Factoring it out, we'll have here 2y minus 1. And inside we have y squared minus 9 equals 0. Y squared minus 9 is simply difference of two squares. So this one will be y plus 1 times 2y minus 1 times y minus 3 times y plus 3. And from here, all of our factors are already linear factors. So it's easy now to obtain the values or the roots in this equation. So we have either y plus 1 equals 0, 2y minus 1 equals 0, y minus 3 equals 0, or y plus 3 equals 0. Simplifying in these linear equations, we obtain y equals negative 1, y equals 1/2, y equals 3, and y equals negative 3. And so these are our roots for this higher order polynomial equation. So again, it's quite a lengthy process, but I'm sure that by practice and by enhancing your skills in factoring polynomials, this process will get much easier. It just took a bit more time in this video since I tried to go in depth on the methods and the techniques that I use in achieving this. And so we end this one with an exercise. You can work on solving this. 4z raised to 6 plus 8z raised to 5 minus 17z raised to 4 minus 42z cubed minus 16z squared plus 10z, oops, don't have space, plus 10z plus 5 equals 0. So I leave this to you as an exercise, and as a hint or the sketch of the solution, you'll first obtain a factor. Say that factor is z equals negative 1. So z equals negative 1 is a factor. So you can use this and apply synthetic division. After applying synthetic division, you'll apply factoring by grouping. After applying by factoring by grouping, you'll apply substitution, or the one that we did in the first example. Substitution plus factoring quadratic trinomial. In this quadratic factoring quadratic trinomial, you'll apply specifically the slide and divide method. And after that, you'll substitute back. And lastly, there will be one out there wherein you'll apply the difference of two squares. But of course, you may have a different solution to this one, but if you're kind of lost, you can try to apply this sketch in solving for this problem. So that's it. Feel free to comment down below your solutions, your answers, or your questions regarding this problem and this topic in general. So that's it, and that is all for this video.